Boys and girls. Boys and girls. Laugh. Laugh. Let us begin. Let us begin. So, for our quandary, the bullet slams into the block of wood. I'm hoping that this is, not a difficult problem for us at this point, and that you drew a little cartoon, or is already drawn for you. Bullet moving, block not moving. All right, this guy's sitting still. Can we take a moment to stop thank you. Okay, so I think what we've got here is we've got 0.1 kilograms going 560, yeah? And then here we've got, well, if that's 845 grams, I think we've got 0.945, is that right? Combined, going some velocity like that. So this is about as simple as you could make a momentum problem. Yeah. Yeah, but when the bullet sticks in it, it's 0.945, right? Times. And that's why they pay me the big money. I've got a degree in physics. It doesn't matter, you'll get the same velocity, but if you're trying to calculate joules for the energy, you really definitely want to use kilograms. Otherwise you'll get something else. Some unit that nobody else uses. Okay, so the velocity I'm getting here is that the velocity is 59.259. And then this is very cool. 259 appears to repeat. What are the odds? Yeah? Are we good with that? How many people were able to get that? Let's have a little thumb. There we go. Thumbs up. There we go. All right. So this is wonderful. If you could get that, that's wonderful. Then the kinetic energy before is 1/2 times 0.1 times 560 squared. And this is why bullets hurt, right? This is a huge bullet. This is like probably one that would hunt an airplane or something like that. Okay? I mean, seriously, a bullet, there's like grams, 2 or 3 grams, 4 grams is a big one. Okay, this is 15,680 joules. Yeah? So if we calculate the energy after, are we going to get the same energy? Do we get the same energy? Did anybody do it? No, you don't get the same energy. We may have discovered the eternal flaw of physics, right? The kinetic energy is not the same, right? So let's look at the energy after. That's going to be 1/2 times 0.945. So it's more mass, but less velocity, right? So 59.259 repeating, right? So let me get that answer there. I'm going to square it, and I'm going to multiply by 0.945. And especially when you're using something that's squared, right? You want to be really, really careful you don't round it, because that really affects the answer. But still I get 1,659.25. Ooh, this is really strange. 259 is repeating. Is that true? Yeah. Whoa. What is that? Did anybody get that? If you seriously try. I took the same answer from my calculator. Yeah. There. Okay. Okay. So these is not like 666. So is this the same? Is this approximately the same as this? No. That's about the same, isn't it? No. Is it like 1/10 of that? Yeah. So here's the question. The trick is momentum conserved or is energy conserved? It's a trick question, right? Because it's not a choice. They're both conserved. What's the trick? Why is kinetic energy not conserved? It goes, well, it didn't swing up. We're going to do that. We're going to, we'll get out the dart gun and it'll swing up there. I don't think it went to potential, right? Yeah, I'll bet that this bullet, some of this energy, I mean, for sure it's conserved. The energy is conserved. It just didn't turn into kinetic energy. I'll bet there's some heat involved. Yes? In fact, when you look at lead bullets melt when they hit things, right? You look for little spatters of molten lead when lead bullets strike things, right? So yeah, these get really, really hot. The bullet will get really, really hot. Well, but you would think that would turn into work and turn into right. But the notion here is that there's an irreversible thing going on. This is an inelastic collision. It's tearing a hole in the block of wood, right? It's doing work to tear a hole in the block of wood. Ultimately, that's turning into heat and noise and stuff like that, right? So that's the notion here, is that in an inelastic collision, okay, in an inelastic collision, oh, thank you. You've saved me. Let's have a little applause for the savior. Now I've embarrassed her. I'm sorry. All right. Did she have anything like sarcastic to say about me? No. Okay. She'll say it to me later. Megan's got a question. No, you're just stretching. Oh, okay. There we go. Okay, so let's just point your eyes over here. Okay, there are elastic collisions and there are inelastic collisions, and this is just sort of my first. Just exposing you to this, right? An inelastic collision. This is an extreme example, right? That they hit and they possibly stop. If I could ever get that collision just right, okay? These guys could hit and just stop. Now, if you notice, they sort of clank and they shake like that for a while. I'll bet the energy is going into like air friction and stuff like that. It's heating up the room. But for sure, momentum is conserved, but kinetic energy is all turned into heat. So that's an inelastic collision. I can show you an elastic collision. It's very hard to say these things. Here is an elastic collision, one that is elastic. It's impossible to say this. It's impossible for me to say this, right? They're like, don't like each other magnets. You like that? I like this. This is fun. Okay, we heard it hit something there. It's like, isn't that fun? Okay, so molecules, when molecules bump into other molecules, those are elastic collisions. Magnets and things like that are elastic, and that's because they're called that because it's elastic. Stretchy, bouncy, yeah. All right. So anyway, that's, let's do some more conservation of momentum. Let's do energy and momentum, and then I don't think we're going to need much more than 20 minutes. So aren't we out of here at 11:05? Is that all right? So this would be 20 minutes. Let's just say that the battery is good if the needle falls right there. Something like that. I don't know. Battery testers, little needle, green zone.
Oh, okay.
Your fire extinguisher. I don't know. I'm in a very strange mood. So. Just hang on. All right. The quandary. It is a quandary. All right.